Any questions, any burning questions or thoughts? How's the homework? How's the exam? Yes?
Do you think we're gonna get our midterm 2 results back in time to study for the final?
I hope. So my goal is to have them, yeah, so let's talk about that for a second. Maybe we should pull up the syllabus, just so that we're kind of on the same page. Okay, so we are here. No, we are here, session 19, okay? And there should be some questions due tomorrow, but we're gonna do more circle today, and then we'll cover absent max shear stress. Depending on how quickly I can get through things today, tomorrow, and Thursday, I guess. Actually, Thursday probably not. So it's today and tomorrow. We're gonna try to get over to the lab to finish it up. Okay. There's one more set of experiments I'd like us. Well, they're kind of a pair of experiments that I'd like us to be able to do for the lab. Some of you have done parts of the lab, and I need to go and I need to grade some of that. I need to grade some of the FEA. But please, this would be a good weekend to do that. The final exam is on the last day. So we're going to celebrate Independence Day with an exam. Fortunately, of course, you have all evening. There should be no fireworks during our exam time. Okay? I'm sorry. You're not the only one that was kind of, well, we're all in it together, so to speak. All right? That's kind of the schedule. But yes, I should be able to get you your digital versions of your exam Saturday night. That's my goal. Okay? So Saturday night, I should be able to do that. Yes?
I thought the final was at 10 a.m. at some point. I still during class time.
Do they publish a set of, I mean, does anyone else know of another final time? Okay, I didn't know of it. You go ahead and send me the link, because I know Rutgers publishes the finals, and that's what I look at it for the fall and the spring, but I didn't look at it for the summer. So I was just thinking we were going to do it on the last day of class. Was it going to be on the last day of class?
I don't know. I just remember reading that it was at 10 a.m. So
Okay.
I'll check again.
It would have to be unanimous consensus that people wanted to do it earlier, all right? Because right now the syllabus is, we've been sticking to it, and so that's kind of what I think people have been planning. Okay, I could see why people would want it earlier in the day, and it wouldn't make much of a difference to me. So if there were like a unanimous consensus that said you wanted it earlier, I don't know. A lot of people probably be studying though, to be honest, in that morning. So I think we'll just probably keep it where it is. All right. So yeah, make sure you do the lab module and here, and then we need to do some final experiments in order for you to be able to complete that. All right. Today we have the opportunity to continue our discussion on plane stress, and we're going to pass through a rite of passage, essentially. This rite of passage, I guess some of you already went through it. Dylan, you said you went and you studied this?
That was me yesterday.
Both of you? Okay, so just, I hate, that's so sad because, okay, I have been sticking to the syllabus, folks, all right? So, right, the syllabus, all right, just so you know, okay, so the next thing, we will have class on Wednesday, all right, the day before the final. You will not be responsible for that material though. Okay, the exam will go through session 24, all right? Just like, so I kind of tried to specify which sessions you're responsible for. I know we have previous exams that have stuff that's a little bit different. Okay, nonetheless, we're sticking to the syllabus as it is right now. Yes?
Is the final cumulative?
Yeah, it will be, nonetheless. So, okay, so here's the story. How long do you normally have for a midterm exam? in the semester? An hour and 20 minutes, right? How long did you have for these? 2 hours, right? How long do you normally have for a final exam? How long do we have for it here? 2, right? So yes, it's cumulative. It's cumulative. Nonetheless, there's even less time for the final than there normally is, and we should probably try to cover some of the most recent material. So it's going to be cumulative in terms of you can't really do, I mean, a lot of the stuff, like you couldn't do a lot of the stuff in exam 2 if you couldn't do a lot of, if you didn't have the background before, right? So that, in that sense, but it will, you're going to see more on Mohr circle for sure, 100% sure about that. And we'll talk about failure criteria. And so those are going to be important to know, and then we'll get into beams again. Okay. So those, yeah, so it's going to focus on those. We only have 2 hours. We don't have the full 3 hours. Okay. Okay, where are we? So we are back here. Okay. So today we're going to discuss Mohr circle, its derivation, the methodology, and its application with examples. Okay. And after this, you'll be able to commiserate with mechanical, aero, civil, I don't know who else, biomedical, anyone who does anything with structures, pretty much engineering-wise, knows what Mohr circle is. And it's this instant visualization tool that, I don't know, maybe some of you felt was helpful on exam 2, maybe not. It was? You thought it was? Because I was, yeah. For problem 2 on the exam, I was thinking in terms of Mohr circle. I was like, I know this is what it looks like because of Mohr circle, not because of this other stuff. But of course, you do the derivation as we explained, and if you put Mohr circle on that exam,
you told me not to.
Yes, no credit for you. So not no credit, probably 0.25 out of 2. Okay. So I had almost written, if you use another method, you will only get 0.25. But then I was like, why do I have to explicitly state that? That's mean. So now I'm explicitly stating it. But that's mean, right? So anyway, this is something that will allow you to look at your finite element analysis, look at its results, and be like, bam, all right, now I have a better idea of what's happening. But right now it looks like a bunch of scribbles, okay? But we'll go to what these scribbles mean. Okay? So as a review, we can use the slicing technique to be able to figure out what the state of stress looks like for a rotated element. Okay? And we've discussed how rotation of a tensor changes these, sigma x gives us a new sigma x prime, sigma y prime, tau x y prime, right? But we haven't lost the information, okay, in a rotation. So I could rotate it back, I can rotate it to another angle. The information, the content there is still preserved. We talked about these equations, this general form of plane stress transformation, and the 3 equations that you can use if you do not want to do the method of slices. And today, or now this week, in most cases, what you'll be able to do is not even think about these, but use Mohr circle. Okay? And we've also talked about the max and min in plane principal stresses. In plane, big deal. All right? We're going to talk shortly tomorrow about what happens in the 3rd dimension. And it's very simple once we know how to use Mohr circle, okay? But this is not the same thing as the absolute, okay, max or min for stresses. And we're going to cover that tomorrow. And with Mohr circle, it goes back to someone named Christian Otto Mohr before the 1900s. 19th century, and essentially this is a methodology, a graphical methodology based on geometry or trigonometry to be able to visualize what happens to the state of stress for an element under rotation. Okay, so it's a visual way to come up with rotations, and it's not too dissimilar from what you do in pre-cal or trigonometry, where they teach you the unit circle, right? And it's like, oh yeah, now I know how to calculate the sine of 45 degrees. Now I know how to calculate the sine of 60 degrees. Now I know how to calculate the sine of, or the tangent of whatever, right? It's the same idea. I rotate an element, okay, and then I look at the unit circle. I rotate by some angle, and I look at Mohr's circle instead of the unit circle, and I can tell you what's happening to the state of stress. So the derivation is actually not that complicated once we use the general equations that we have for sigma x to sigma x prime and tau xy to tau x prime y prime. So you start with two of these equations. So there's one for sigma x prime, and there's one for tau x prime y prime. And then you move one part of this equation. You move this over to the left side, like you see here. Okay, so this is just using the first equation, and so now we have this quantity over here and this quantity over here. You square both of these equations and you add them to each other, and you get this big monster of an equation. And now we can simplify this equation. You see that this expression and this expression right here, they knock each other out. Well, actually, no, they don't. They don't. Actually, there's some algebra that happens. They don't exactly knock each other out, but you can begin to see that we can simplify the expressions that we have here to get the following. Okay, with these cosine 2 theta terms, sine 2 theta terms, and things of that nature. Okay, so this is the equation. And you're like, well, it's still an equation. What's the format? What's the standard form for a circle on Cartesian coordinates on an xy plane? Forget what you see here. Just what's the standard form? Yeah.
X squared plus y squared equals r squared.
So x squared plus y squared equals r squared. Exactly, right? And if I want to specify a center that's not at the origin, what do I do? So what you just did is x squared plus y squared equals r squared, right? That's right at the origin, right? So what do I do? How do I modify it?
X plus or minus something squared.
Right. So like if I wanted it like at 1, 1, right? It'd be like quantity x minus 1 squared plus quantity y minus 1 squared equals r squared, right? Okay, so it turns out we only care about the center of our circle on the x-axis. Okay, and that's this derivation here. So Mohr's circle is just going to shift right and left for us. Okay, it's not going to go up or down. Okay, now, yes, we care about the z component, but just in terms of where the center is. Okay, so if you look at this, and let's say that the right side is a radius squared. Okay, this right side is a radius squared. So this over here is radius squared. What then would we use? And you said, you have this x minus something squared plus y, or we now are saying it's going to be y minus 0 squared. Okay, so what would be the, based on this, this is r squared, right? And these are knowns, right? Because I give you a state, sigma x, sigma y, tau xy. So I know what, or at least if I were doing it the conventional way, here's a state, now rotate, okay? So then the kind of things I'm trying to solve for would be sigma x prime, sigma y prime, tau x prime, y prime, right? So on this side, what would you call the two axes? What would the axes be, right? So, you have, right, we said x squared plus y squared equals r squared. So the two axes are x and y. So if you look at this now, what would you say are the two axes?
Sigma and tau.
Okay, so sigma and tau. That's right, okay? And in particular, you could think it's like a sigma x prime, right? And you could think of it as a tau x prime y prime. All right, but sigma and tau, and it turns out there's a relationship between sigma x prime and sigma y prime. Okay, but yes, the two axes that we're going to be interested in are the sigma and the tau. So normal stresses and shear stresses. And this is, right now, what we're doing is in 2D, okay, because this was a 2D element. So this x-axis is going to be having a sigma, as Eric said, and the y-axis we're going to put in a tau. Okay? And what's this? Where's the center of this circle? Where would the center of this circle be? Yes. I'm sorry, Matt. Sorry.
Sigma x plus sigma y divided by 2.
Yep, that'd be the on the horizontal axis, we'll say.
Yeah, y is 0.
Yeah, that's right. Okay, that's it. Okay, and then what's the radius? We said the radius was the square root of this entire term on the right. Okay, so that's what we'll call the x offset. Okay, from the origin. This is what we call the radius, or the radius squared, right? The square root of it was the radius. Okay. We have this term right here is really just the average of the sigma x and the sigma y. Okay. And so now we could rewrite this equation like this. I mean this equation like this. And we can say that the center of the circle is at this sigma average comma 0. And we can say the radius is this quantity like that. All right, so we've done a bunch of work with equations, but we know that these equations do correspond to a circular geometry on Cartesian coordinates. Okay, so now, how do we relate this equation of a circle, okay, to a graph? All right, and how do we think about these equations in terms of what we've been discussing? Well, this is the original element. Okay, so backing up here, right? This is the original, standard. This is what I give you. This is state of stress, and I've got an xy coordinate system, and sigma x aligns with x, sigma y aligns with y, right? Tau xy is going to be describing these stresses that are parallel to the surfaces of the material element. And then I've got a theta, which corresponds to some rotation. Okay. Now, the things that should be obvious based on the previous slide in our recent discussion are, here is how we find the origin. We take the average of just sigma x and sigma y, and that is going to be where the center of the circle is. Okay, it's better, well, I said origin, but how do we find the center of the circle relative to the origin of the coordinate system? I guess I should have said. Okay, now, the radius we also have as this equation right here. And this, so you could just go ahead and draw this R, and that's a little bit abstract. Okay, but that's fine. Because like, okay, I don't really know what this is, but I'll just draw the R, and then I draw a circle, and you call it done. All right, that's fine. So now you got a Mohr circle. And we're going to go into more detail here in a minute in terms of the methodology. But one thing that hasn't been clear from these equations so far is where theta went. So if we go back to the previous slide, I glossed over this step, but there are thetas in our equations of transformation, and there are thetas when you do the slicing, right? So we've got to discuss where these thetas, or how these thetas get used with Mohr circle. Okay? And we're going to discuss that in a little bit, or right now. I can discuss it right now. I'll say, generally speaking, a counterclockwise rotation in theta, with the way we've shown to do things, corresponds to a 2 theta counterclockwise rotation on Mohr circle. Okay. And that's the way, I said, the way we do things. Okay, so we still haven't exactly said, hey, what is this point P yet? I mean, we'll get into that in a minute when we talk about the methodology, right? But what we're saying right now is that counterclockwise rotation results in a counterclockwise rotation on the circle of twice what it was of an element. Okay? And we're going to end up picking off points on Mohr's circle that correspond to states of rotation. Now, if you look in different textbooks, okay, what you'll find, okay, is that there are different conventions that people use. Okay, so just, this is for your good to know file, all right? And maybe to help us not get too confused, all right? And help us remember that, yes, if I rotate the element counterclockwise, I better go counterclockwise on Mohr's circle. But if you use a different convention, right? And what are these conventions? We're talking about what we consider to be like a positive tau xy, right? What we consider to be a positive sigma x, what we consider to be a positive sigma y. Okay? And also very importantly, what we consider to be a positive tau. So you see in convention 2, and I kind of skipped over this, we actually, to keep counterclockwise with counterclockwise, we actually draw a positive tau downward. Okay, so I kind of glossed over that, but here, do you see there's this little arrow here? This is downward. Okay, so this would be a positive shear stress down here. This would be a negative shear stress. And you realize that's kind of, it's positive and negative shear stresses are not the same as positive and negative stresses, right? We talked about how compressive stress and a tensile stress, they can have different failures based on their magnitudes, right? The sign, better said, the sign can influence whether it's going to fail or not for a given magnitude, okay? Because materials will behave differently under compression versus they will under tension. But shear stress, not so much, right? The rod doesn't really care if I twist it this way or if I twist it this way, okay? But anyway, for our convention, tau is downward, all right? Don't worry, we're going to have lots of opportunity to draw more circles. Okay. So here is kind of a first pass. This is a homework question, all right? So it says, if an element has sigma x equals 100 megapascals, sigma y equals 50 megapascals, and tau xy equals 10, what are the coordinates for the center of Mohr's circle, and what is the radius of Mohr's circle? So even before, you don't even have to do any drawing at this point. It's just tell me where the center is. So where is the center, folks?
75.
Right, so the center is going to be at sigma x plus sigma y divided by 2, the average of them, comma 0. Always comma 0, okay? And so, like Eric just said, we take the average of 150, and we get 75. And yes, we should be careful like that. Okay, so that's where the center is for this particular case. What's the radius? Okay, well, for this, we can go back to this equation right here. Okay, so we'll get into a more kind of graphical way to do this, but if this is what you're given, or if you're just given those, if you don't want to draw the Mohr circle, essentially, which is what we're kind of asking you to do at this point, or what I was asking you to do, you just plug this in. All right, so it's going to be, whoops, where did it go? Okay, so the radius is going to be equal to the square root of, it's the difference now of sigma x and sigma y. It doesn't matter if I do sigma y minus sigma x, right, or sigma, it's just the difference because they're going to be squared, right, over. So here in this case, I've got 100 minus 50, that's 50, 25. So we've got 25 squared. And then this tau xy is 100. Well, it's sorry, it's 10 squared, but it's 100 underneath. Whoops. Okay, like that. And I don't, do I know what this is? Yeah, actually I do. I have it here. It's about 27. Okay. So this is just to kind of set the stage, all right? We've got a circle that we're saying is at 75, right? So this is going to, we'll say this is the center, and it's at 75, 0. And the radius, it's smaller than 75, right? So it's not going to cross the origin. It's going to do something like this. Okay? And that's all we're doing at this point. Okay? I guess I can also draw the axes, right? Which is typically how we draw them. We do a tau and a sigma. Okay. So what is the procedure here? First, we're going to draw the axes, okay, with sigma on the horizontal axis and positive tau going vertically downward. So we already said that. So we have sigma, we have tau, and usually we know that they're going to be symmetric. The question is, usually, do I draw a lot on the left side, like on the negative side of the tau vertical line, or do I draw a lot on the right side? You know, it's kind of like when you're drawing your shear force and bending moment diagrams. You're like, hey, do I need a lot of, what do I need a lot of when I'm doing them? Like, do I need a lot of positives? Do I need a lot of negatives? In this case, it's mostly, do I need to draw a lot on this side, or do I need to draw a lot on this side? Okay, the next step is to go ahead and plot the center of the circle. And this is pretty straightforward. It's just the average. It doesn't matter what tau is, okay? And it's beautiful. It doesn't matter really what sigma or x or sigma x prime or sigma y prime are, right? This is transformation. So I can take, any sigma x prime plus any sigma, pairs of sigma x prime and sigma y prime. Or I can take the original sigma x and the sigma y. They all should give me that average, which stays constant. That's where the center of the circle is. Okay, so there's the average. And, it's, if you like, you can make a little dotted line like so. You don't have to do that. There's going to be many opportunities for like little dashed lines and things that we're going to draw. Okay. Now, this is the part that I didn't tell you yet. We plot a reference point. Okay? What is the reference point? Now we're saying, okay, you were given a state of stress. You were given sigma x, sigma y, and tau xy. Typically, you're going to plot sigma x. You're going to ignore sigma y. Typically, okay, and we'll get into this. But you're going to plot sigma x and tau xy. Okay. So what does that look like? This is what it looks like. See, this is the sigma axis. This is the tau. Each point on these circles represents on a Mohr circle. Each point on a Mohr circle represents a state of stress. Okay? And in this case, now I've pinpoint a state of stress on the circle corresponding to what was given to me as sigma x and tau xy. Okay? We'll talk about this later, but anyone want to guess? Where would I plot, instead if I wanted to plot sigma y, because I didn't plot sigma y here, where is sigma y on this plot? Yes?
It's
one radius away along the same line.
Yes, so it's 180 degrees, all right? So this is P. If I wanted to call this Q out here, okay, let's see. Let me draw the rest of the circle, okay, first, and then I'll go back and talk about this. So, yeah, this is where sigma y okay, would be, all right? We'll talk about that a little bit later in more detail, but just intuitively, what is the angle between x and y? Between any coordinate axis and another coordinate axis was 90 degrees, right? So if 90 degrees, right, on an element represents 2 times that, that means that this point over here is 180 degrees from where this point is. Okay, and that's where we plot sigma y. And now if you go 100, if you take an element and you rotate it 90 degrees, then you are essentially flipping the tau xy. Remember that? Remember we said if we start with a right, you're getting bored of these, right? Aren't you getting bored of these, right? This is sigma x, this is sigma y, and this is tau xy, right? But if I rotate 90 degrees, okay, then my new, so I didn't, I'd make another square here, right? What's the state of stress here? Well, I rotated 90 degrees, so the arrows are still all in the same spots, okay? Because, well, I'm still, I could cut this, I could do a slice or whatever I want, but 90 degrees, the actual stresses are all in the same places. But what has changed is now sigma x is coming out of the top, and sigma y is coming out of the side, that on the left side. Do you see this? This was a rotation of 90 degrees. And now, tau xy, right? Tau xy was over here, right? This was the positive x face. Where's the positive x face now? Positive x face is this one, and positive y is this direction. Okay? You see, it's so this would be the positive tau x prime y prime essentially. Okay? It would be going this way because it's how it's oriented by its subscripts. Okay? So now, look, that original stress that was going that direction, it's going the opposite direction of the new tau x prime y prime, which means it's negative. Okay? So anyway, maybe we're jumping ahead a little bit, but the point is that when we rotate by 90 degrees here in an element, that corresponds to 180 degrees on Mohr's circle. Now, how do we figure out the radius? Without looking at the equation and using your skills from geometry, not even trigonometry, how would I figure out the radius of the circle? And what I should say is, going back to, I know C and I know P. How do I figure out the radius? I know that P is on the circumference of the circle, so how do I figure out the radius? If it's helpful, you can look at the equation, but yeah, Isaac.
Can you just find out what is so find the slope first,
Okay.
and then you can find out the distance between the P and
Okay, so yes, so you could figure out a slope. So if you're figuring out a slope, you're kind of suggesting maybe there's a trigonometric way to do it.
yes.
I'm saying let's just go back to high school geometry. Well, I guess trigonometry is also high school. But how do I do it with...
Don't you do the triangle?
Yes, it's just... Okay, what is it? What is the triangle? What is the radius?
C squared equals C squared.
Yeah, it's the Pythagorean theorem. That's all it is. A squared plus b squared is equal to c squared. All right, so I want to figure out the length of the hypotenuse, and what do I know? When I plotted P, P was sigma x tau xy. I now know maybe this is the A, right? This is one side, and this is the other side, and if I do the square root of those two, squared, the sum of the squares, right, is equal to the square of the hypotenuse, then I can figure out what the radius is. Okay, so once you've got this, you can figure out what the radius is. And how do you do that? Well, you say, well, okay, this horizontal component is just sigma x minus sigma average, right? That's all this is. This length right here is sigma x minus sigma average. Okay? And what is this vertical component? Well, that one is just, it's already written, it's tau xy. Right? So the radius is going to be the square root of sigma x minus sigma average squared plus tau xy squared. Right? This is just the Pythagorean theorem. Okay, that's it. So you see, besides knowing that the center is at the average of sigma x and sigma y, and besides knowing that tau goes down and sigma goes to the right as positives, and besides knowing that, you know, every state of stress corresponds to a point on the circumference of the Mohr circle, that's the only equation you really have to know, is that sigma x plus sigma y over 2 is where the x coordinate is for the center. After that, you can do the rest by geometry. Okay. Will you write these equations on your formula sheet? Of course you will, because that's what we do. Okay, but you don't really need to. Okay. All right. So, what can we do with Mohr's circle? Okay. So I jumped ahead again, right? And you can see I jumped ahead here too. So let's just erase it. Actually, I don't think it will let me erase it. That's okay. It's there. We can find stresses in an arbitrary orientation. Right? So this is saying third method of figuring out the state of stress with a rotation. Right? The first method was do the slicing, which you got to do yesterday. Okay? And then do use the general set of equations, which you got to do yesterday. And then a week from Thursday, you'll get to do Mohr's circle. Okay? And we're saying that we rotate by 2 theta, all right, to get the same state of stress as if we were rotating the element. Okay, so here you've got the opportunity to write out your sigma x, your sigma y, right? So all these things. Okay, and what we're saying is, if this was your original state at P, okay, and you have a radius, you know, r here, and now I tell you, okay, go ahead and rotate by 15 degrees. Okay, what you do is you say, all right, well, if you told me to rotate counterclockwise by 15 degrees, all right, the positive, then I'm going to rotate 30 degrees on Mohr's circle. Okay, that's where this 2 theta comes in, like this. And then we're going to figure out what the new P prime is. This P prime corresponds to a new sigma x prime and a new tau x prime y prime, which are on the Mohr circle as well. Okay? Any questions? This must seem a little foreign unless you've been studying this, but do you have questions in terms of what we're doing here? How would you figure out the new sigma x prime and the new tau x prime y prime? Huh?
Trig.
Yeah, trig, right? Because what? Because you've got, say, some angle. So you rotated this amount, but originally you had some angle here to form a right triangle, right? Just like we were doing with the Pythagorean theorem, right? It was a right triangle. So you figure out, okay, where I was, right? And then you figure out what the angle is here, and then if you do 2 theta, now you've got another right triangle, right? That you can draw another right triangle from like here to here to here, and this would be some new, let's call it phi, okay? And you can figure out what the length of the opposite and adjacent sides of that new triangle are, okay? So this is, again, it's a method for using trigonometry, for using geometry to figure out what the state of stress is for any given rotation in 2D. Now, how do you figure out principal, okay, not principled, in the in the sense of I have principles. Hopefully, I have some principles. But how do you figure out state of principal stresses? What do you think? Well, first off, what were principal stresses? What did we discuss? I know it wasn't covered on the exam, so it's not fair game, right? But you've done the homework on it now.
When the shear stress equals 0.
Yeah, when the shear stress is equal to 0. So when is the shear stress equal to 0?
Sigma max.
Okay, so sigma max, or like you were drawing, when you're on the horizontal axis, right? Because the shear stress goes to 0. So we're going to have principal stresses that we can think of when we look at the horizontal axes, okay, or the horizontal axis, like this. And we look for an orientation that would get us to that horizontal axis. And we call that rotation 2 theta p, right? Because this p stands for principal. So we go like this, 2 theta p. And remember, I kind of said, hey, we introduced this idea of sigma 1 as being the largest principal stress, and sigma 2 being the next in line. Okay, and there will be a sigma 3 for the third dimension in a little bit. Tomorrow. But this methodology quickly allows us to identify what the principal stresses are. If you know the center, okay, so again, without using an explicit formula, which we did give, right, for calculating principal stresses, and which you did hopefully use on the homework, or you made a graph and you picked a point. What is a formula for sigma 1? Yeah.
Radius plus the center of the circle.
Yeah, it's just the radius plus the center of the circle, right? And sigma 2 would be,
Radius minus.
well, the center of the circle minus the radius. Yes, right? Over here. Okay. When we say radius or center of circle, right, we're talking about the x component. Okay? And yes, foreshadowing, maybe not enough. How do we find the maximum in-plane shear stress? Huh?
It's the radius.
It's the radius, correct. Okay, and you see that? Because the radius is going to dictate when you have a maximum. Like, so here and here. So this is going to be the maximum positive shear stress down here, okay? Because that's positive down here, right? And this one would correspond to a maximum negative or most negative shear stress up there. Okay? But again, right, they're going to be 90 degrees off from each other, which corresponds to 180 degrees off from each other in Mohr circle world. Okay, or they can correspond. Okay, so or it can correspond to tau xy max and minus tau xy max. Okay, just like we were talking about. Okay, how and previously we kind of glossed over it, but let's talk about it again. 180 degrees, right, will give us a sigma y prime, and it will also give us a minus tau x prime y prime. Okay, you see that? So this is for any state. Like if this was p, right, this would be the sigma x comma tau xy, right? And so I go over here, this is the sigma y comma minus tau xy, right? 180 degrees off. What's 100 degrees? It's this purple line to this poorly drawn afterthought on the slide red line here. Okay, so this is supposed to be 180 degrees. And if I go to this is even worse, and this was done beforehand. This is a new state of stress with a rotation of 2 theta here on this black, and this is supposed to be 180 degrees to this other black dot over here, which corresponds to sigma y prime minus tau x prime y prime. Any questions? This is your rite of passage into mechanics, Mohr circle. And you're like, why do we still teach this? Because it's very useful to visualize quickly what the maximum shear stresses are going to be and what the principal stresses are going to be. That's the real power. Okay? So, you know, you give me a sigma x, you give me a sigma y, at least in 2D. Okay? You give me those, and I'll be like, I know almost instantly what the maximum shear stress is going to be. Okay? And a lot of materials fail because of shear stress, the ductile ones. So here's an example. If we have stresses in an arbitrary orientation with sigma x equals 100 megapascals, sigma y equals 50 megapascals, and tau xy equals 10 megapascals, and we rotate the element 30 degrees counterclockwise, what are the resulting sigma x prime, sigma y prime, and tau x prime y prime? And now you're like, I programmed in my calculator for the last exam. I'm just going to use the general set of equations. Okay, yes, you can do that. All right, you can do that. Instead, though, we're going to try to apply our newfound knowledge and use Mohr circle. Okay? So, what are the steps? What do you think we should do? What would you do? Any thoughts? Yes, Andrew?
I draw the center.
Yeah. Okay, so where's the center going to be?
150 divided by 275.
Yeah, 75, right? Okay, great. Then what are you going to do? Yeah, go ahead, Nasir.
Plot the reference point.
Yeah, so plot the reference point, right? Which is going to be, we're going to say sigma x comma tau xy. Right? So it's going to be a reference point at 100 comma 10. Okay? Now, on the plot, we can think of quadrant 1, 2, 3, 4. Where is that reference point going to be, right? For Cartesian coordinate system, right? You're all familiar with quadrants 1, 2, 3, 4. Which quadrant are we in when we plot that reference point? 4. Yeah, we're in quadrant 4. Okay, because it's below, but that's positive. Okay. Then what would you do? I think you said it before.
Find the radius.
Find the radius, right? How do we find the radius?
It's going to be the x value of the
Yeah, yeah,
x sigma minus the x value of the center of the circle.
yeah,
And then square that, add that to tau xy squared.
Right.
And then find the square root.
yeah. That's right. So now we know the radius, right? And then what would you do next? Okay, you draw the circle. Yes, yeah. Okay, so you got to draw the circle. What's the prompt asking us to do?
Rotate the element 30 degrees counterclockwise.
Yeah. So what do you need to do?
Rotate it 60 degrees.
Yeah. So we need to rotate it 60 degrees, and it's probably a good idea to figure out what the angle was before we rotate it. Right? You don't have to, but right. So what's the angle we're going to be looking at? Well, the angle is going to be based on what? How would you figure out the angle, the original angle for the state of stress? This is kind of fun. We're just talking it through, not drawing. We'll draw it in a second. But how do you figure out the original angle?
We do it inverse tan.
Yes, of
The sigma x and sigma y. No, not sigma y, the TXY.
yeah. So you're gonna have the opposite side being tau xy, and you're gonna have the adjacent side being sigma x. But there's a catch. What's the catch?
Yeah.
Well, it really corresponds to a 2 theta, all right, on the Mohr circle. So you're going to draw it on what you're going to do is you're going to draw and put just, it is in fact that angle. So the inverse tan, all right, of tau xy divided by sigma x, whatever that angle is, right? But then when you go to the 30 degrees, right, I think someone already said it, you actually go 60 degrees, okay, to the new location, okay, because it's 2 theta. All right, so what are we talking about? Let's now, and then after you've done that, right, then you can use essentially trigonometry if you want to figure out, because you know the radius, and so you can figure out where the new sigma x prime and the new tau xy prime are, or what those magnitudes are, based on the radius and the angle. Okay. So here we go. We draw the axes. We plot the center of the circle like that, and like I think the Matt or the Andrew. Andrew. Okay. Well, Andrew, you said it was 75. Good. We plot the reference point like so. We said it was 100, 10. All right. And then we figure out the length and the radius r. Okay, we'll figure out what radius r is. We draw the circle. Okay. And we have, I guess this is the same one as we got before, 27 megapascals. And then we need to rotate by 2 theta. So this is true, all right? So we can rotate by that, 2 theta, to figure out where we are. And again, I'll argue that we need to know what that original angle is, okay, so that we know where we went. Okay. So phi is that original angle, and that's going to be the arctangent, right, of the tau xy over the sorry, not sigma x. See, it's a sigma x minus sigma average. Sorry, I said that wrong, but now we see it, right? It's this, it's the adjacent side, the sigma x minus sigma average. Figure out what that is, then we say, okay, we're going 2 theta, so we're going to end up being 38.2, is that right? Degrees above there, okay? That we'll call it gamma, I guess. That's 38.2 degrees. And then we already know our R, and we can figure out what our new adjacent component is going to be with the cosine of that. Okay, so the sigma x prime minus sigma average. Okay. And we do that out, and that's 96. And the tau xy prime, y prime, that's just the minus r sine gamma. And that's because what? Because now we're above, and that's a negative terrain. Okay. Good. So that's how we figure out what tau x prime y prime is. And if we wanted to figure out what the corresponding sigma y prime is, that would be looking at this point out here. Okay, so I gotta go 180 degrees over here. All right, or I can think, oh, you know, before I said that it was sigma x, this right here is sigma x prime minus sigma average, right, to get over here. And over here, okay, it's going to be that this sigma y prime is the sigma average minus the r cosine gamma, right? That's going to tell me where I am over here, and that's 54 megapascals. Okay. Any questions? Sorry, I was going too fast when I said that it was just sigma x. No, it's the sigma x minus the sigma average. That's going to be the adjacent part of these triangles. Is it, if you have the transformation calculations programmed in your calculator, or you have it in Python, and you just have to plug in sigma x equals this, sigma y equals that, tau x equals that, and then angle on a tau x prime y prime, sigma x prime. You know, is it that easy? No. But can you do this with, you know, some intuition? Does it make you feel good inside? Maybe, right? Maybe. all right, so another example. If we rotate the element 30 degrees counterclockwise, okay, what are the principal stresses? Oh, and no. I thought I deleted this. This was a mistake-o. Okay, so here you're given a state of stress, all right, and who cares what the rotation is? Okay, or because we just did rotation to figure out another element. What we're asking is, what are the principal stresses and relative orientation for them? Okay. So to do that, we got to figure out where we are, right? We want to figure out what that point is and what that point is. So again, we know that this like little phi we defined, okay, was 21.8 degrees, and we got to rotate 2 theta p, right, is the amount of rotation that it takes to get to there, and it's essentially equal to phi, all right, and that was arctangent 10 over 25. So 2 theta p, or theta p, is just half, right, 21.8, half of that. So we get that we go to here, okay, and this theta p, that's the actual rotation the element has to rotate, right? So if we go back to this little box on the left, okay, this was the original state. We don't rotate this element by 21.8 degrees, we rotate it by 10.9 degrees. And like, right, so like what we're saying is like this got rotated, you know, and these things are kind of funny to draw, right? But you could draw it like that, and you say like that, right? And this is 10.9 degrees, right? And this is the new x prime. This was the x. Okay, this is the new y prime, and this was the original y, like that. Okay, so now figure out what magnitude is for sigma 1. Well, it's the sigma average plus the radius, so that's not that bad. Okay, and the sigma 2 will be the sigma average minus the radius. So sigma average we said was 75. And the radius is 27. Okay, good. So 75 plus 27 was this. 75 minus 27, that should be like 48 or something like that. Okay, and that's what we see there. And whoops, sorry, that's that. Okay. If we're going to figure out the maximum shear stress, okay, they're good. I did delete that mistake-o. Okay, what is the maximum in-plane shear stress and relative orientation? So here we got to figure out, okay, I want to rotate to get to the top of the bottom. And now I'm going to rotate, if I want to get this line to here, right, to the maximum positive, I'm actually going clockwise on Mohr circle, which means I'm going to go clockwise with the element as well. Okay, so the maximum in-plane shear stress, that was the easy one. As Eric said a few minutes ago, that's just the radius. Okay, the angle is a little bit trickier, right? Because we've got to go with this this 2 theta s now going this direction to get to this location. All right, and you know we can say something like that. So what is this? What is this going to be telling us? Well, we know that the radius is this, and the x component is the sigma average, right? So those things are you know, pretty straightforward. Q prime is also pretty straightforward. Okay. And these are the values. Whoops. Okay. Did I not say the relative orientation? Did I not do this? Oh, come on. Well, let's do it. We got to do it because we can do it, right? So what did we say? We said it was like 21.8, right? So the phi is 21.8 degrees. Okay, so we should do this. Yeah. So this phi, right, that phi we said was 21.8 degrees. All right. And we got to go to 90. So 90 minus 21.8, what is that? That's going to be like 68.2, right? So 2 theta s is going to be equal to 68.2 degrees, right? And we should note that this is clockwise rotation, okay? So this theta s is going to be equal to 34.1 degrees. And, you know, some people, or actually maybe I should do this as well, because of the way we did. I mean, the arrow is defined like this, but other people would say, you should really say it's negative, all right? So, you know, this is really I said it, right? It's really clockwise. So if I think about what's happening with the element, this is the original element over here, okay? Now I'm going to say that I have I had this original horizontal, okay, and then this new, and that looks more like 45 degrees, doesn't it? Anyway, but you'll believe me. This is the 34.1 degrees that you have there, okay? Now, it's also kind of, I should probably point this out, it's also kind of fun to point out what the stresses are here. Okay, so this is where we have maximum in-plane shear stress. Right, so it's pretty straightforward that the shear stresses, okay, and let's be maybe more clear. This was x, and this is x prime. Okay, how would you draw? You tell me. How do I draw the new tau? On that element. What is it? We're at a state of maximum in-plane shear stress. You know, to be clear, I'm asking you to help me just draw. You tell me what to do. Yes, Andrew.
Is it just a vertical line going from the station?
Okay, so I think I've twisted myself to your perspective. I think you meant this, right? That's not vertical, right? That's at an angle, but yes, it's an angle. But you did do the angle with your hand, so good. Okay, where do I draw the other arrows? So on this face, do I draw it to the right or to the left? To the right, good. Because they have to meet. Once I've got the first one, I can do the rest. Which direction does this go, left or right on this face? That's left. And then do I go to the right or the left? Whoops, I lost something. Okay, well, I do it like that. I lost my pointer. There, now the pointer. I don't know why the pointer is back. Okay, so that's correct, right? And you see, this is coming out of tau x, it's coming out of x prime, right? So this is the tau max in plane shear stress, okay? Like that. And it's positive. Why is it positive? Well, the way I rotated, okay, I rotated negative 34.1 degrees. So I moved to here, and this is big time positive because it's down here. All right, so that is what? Just 27, because that's R, right? So the tau max in plane is equal to R is equal to 27 megapascals. Now, are there any other stresses acting on this element?
There's sigma x and sigma y.
Yes, there are, right? Okay, so tell me, how would you draw sigma x?
It's going to be the original original sigma x or sigma x prime? Sorry.
Sigma x prime.
It's going to be along with the x prime axis.
Yeah, so I would draw it like this, right? And this we'll call sigma x prime. And what is sigma x prime equal to?
Going to be 75.
Yeah, it's just the sigma average, right? Which is 75 big ones. Okay? What about sigma y prime?
It's negative 75.
Ah,
No,
good.
It's still 75.
All right. Yes. Okay. So this one over here, right?
It's still a positive sigma, right?
Yes. See. Yeah. This, like, for this going to like this state, right?
Mhm.
It's still going to be a positive sigma y. Okay. So this is going to be like that, which is also going to be like that. Okay. What's that? Any questions, comments, complaints, concerns? Okay. So, element rotation of 90 degrees on Mohr circle. We already covered this. Nothing happens with the lines or with the arrows, right? But something happens with the coordinate system. So we need to keep those things straight. Okay? And you see that sigma x prime is going to be equal to sigma y. We already kind of did all this. Sigma y prime is equal to sigma x. Okay? Tau x prime, y prime is going to equal to minus tau xy though. Okay? And on a sigma tau plot, on a plot for Mohr circle, we can draw this like this. Okay? We did a 90 degree rotation of the element, which corresponds to a 180 degree rotation on Mohr circle. Okay? Again, we kind of already covered this. Okay. So here's question number 2 on the homework. If you have an element that has sigma x equals 10 megapascals, sigma y equals 50 megapascals, and tau xy equals minus 10 megapascals, use Mohr circle to determine the larger in-plane principal stress. Well, here's the bummer-rooski. Well, not the bummer-rooski, just the thing to think about, right? Is that now they give you a tau xy, or I give you a tau xy that's negative, which means that you're actually above the sigma axis, right? So for determining the larger in-plane principal stress, you want to rotate clockwise to get to this point down here. Okay, that's all. So it's going to still be just sigma average plus r. Okay. And if you had drawn it wrong, you would have gotten the right answer anyway. Okay, but we want to try to draw them right. Okay, for this one, okay, the transform to state of principal stress, the angle of rotation is required. So you could say, oh, I can go up here or I can go down here, all right? This is the shorter direction to go. If you go this direction, okay, this is going to be the minus tau max, all right? If you were to go down this way, right, this would be positive tau max. So just keep track of which way you're going, okay? And then question 4, you're going to use Mohr circle to determine the max in-plane shear stress, right? So that one is just the radius, okay? And if an element has that, okay, use Mohr to determine the angle of rotation, okay? So magnitude less than 45 degrees. So since it's negative, right, you're going to want to move to the positive. Okay, or not the positive. You're going to want to move so that you're above, to the most negative. Okay, because this started out negative. All right. So those are some problems you get to do. We get to understand Mohr circle a little bit more clearly. And then we get to do some examples. Okay. So Mohr circle, we already discussed what it can do. It can help us find the principal stresses. It can help us find the maximum in-plane shear stress. And it can help us find the angles. When you take DMC, you're going to use Mohr circle. And, well, if I'm teaching it, I probably will never ask you for the angle of rotation. Okay? But I will ask you, you will need to know what the maximum in-plane shear stress is. You will need to know what the maximum normal, the principal stresses are as well. Okay. Now, if we think about our uniaxial loading, this is kind of like the epitome of our romantic relationship with mechanics. All right. We love this test. We're going to go and do this test in a few minutes. Okay, we're gonna have time. We're gonna go to the lab. All right. We think, or we try to think, that for our linear isotropic material, that the tensile test can tell us everything we need to know. Okay. Well, does it kind of? Yeah, sure. It tells us a lot. What does this thing look like on a Mohr circle, though? What does the uniaxial load look like? All right. Well, this is a uniaxial test. What are the normal stresses? Well, it's just P over A, right? The other two directions are 0. What are the shear stresses? 0, okay? In that particular rotation state. So what does the Mohr circle look like? Well, this is what the state of stress looks like. Sigma 2 is at the origin. Sigma 1 is, well, at P over A. Okay. The average is the center of the circle. So people, what do you think? Does this look like it? This looks pretty good, right? This is what Mohr circle looks like, right? Yeah, okay? Now, where is that point? Where am I? I'm over here, right? I'm on this point right here. This is where sigma 1 is, right? And this is here. So I'm in a state of maximum in-plane, maximum principal stresses, right? Maximum in-plane normal stresses, okay? So what is the maximum shear stress, though, that this material is actually experiencing?
1/2 sigma 1.
Yeah, it is, right? So we're like, wait, whoa, this is where we start to get to some cool stuff. Uniaxial testing, no shear stress. No worries, no problems. But I can take an element in that system and rotate it by a certain amount so that I get the maximum shear stress. How much do I rotate it?
45 degrees.
45 degrees. Why? Because I went 90 degrees either to down here or up here, right? Either way, to get that state, okay? So the average, like you said, is this. Okay, I mean, really, okay, so maybe I should say, maybe this, this is like minus tau. It's one of the reasons why I continue to get confused about this is because, once again, what did I learn, or what did I have to teach well, when I was an undergrad, I had a different book, right, for mechanics and materials. And then when I started teaching DMC, I taught it before I taught this class, and we used Juvenile's book, and they use a different convention. So when you look at DMC, if you use Juvenile's book, tau goes up. All right, so whenever I draw those Mohr circles, I'm like, all right, go up. But I don't care about the orientation so much because the orientation will be flipped. So like when I say orientation, I mean the thetas would be going the opposite directions.
Not you, sorry.
Anyway, the tau max is, as you said, it is the sigma 1 over 2. It's the radius, it's the average, okay? And tau max, you could say is that, if you want, okay, depending on which way you go, 45 degrees, you know, either way, okay? So now, in this case, I rotated, so you see this? I rotated clockwise. Okay, so that means I went from this state to this state. So I went from having a sigma x that was here to a sigma x prime up here. I went from having a sigma y that was 0 to a sigma y prime that is now a max. Everyone see that? So I went from this state to this state. So what happens? Sigma x prime, y prime, I now have my shear stress. So tau max I drew in the opposite direction, okay? Or I could have drawn it in the same direction that I normally would have for my x prime and y prime, but just said it was negative. Can you see that? It's really, the convention would say this is the tau x prime, y prime that's positive, okay? But it's now drawn the opposite direction because it's negative, because it's up here. Oops. Okay. What is sigma 1? Or what is the sigma x prime? It is now sigma 1 over 2. Okay. And what is the sigma y prime? Also sigma 1 over 2, coming out like that. Okay. This is the state of maximum in plane shear. Right? And when the maximum in plane shear, you get maximum in plane shear, but you don't necessarily get that the normal stresses are 0. In a state of principal stress, you get that shear is 0, but it doesn't work the other way. Pure shear. This is another kind of, you know, you can do different types of shear tests if you like on a material, or, you know, these are important for rods, of course. So look, this element, okay, is a little bit wackio. Why? Okay, this is x direction, all right, and let's say that that over there is y, okay, like that. So if this is y, did I not draw it? I feel bad. But anyway, what I drew, or what I meant, is that that's y, okay. Do you see how we've transplanted this element on the top surface to look like this element here? Okay. Now, is tau xy, this is the convention, right? This is positive because this is on the x face in the y direction. Okay. And I can draw the rest of these arrows, right, just like that. And we can say that if we were to flip this, all right, or actually, let's say that's not a, the flip is not the, let's just rotate. Okay, flip actually works too, I guess. Yeah, it's fine. We can leave it as flip because it's fine. But here, okay, we flipped it over, and now this is x over here and y over here. Great. Yeah, it's a flip. Okay, so then when we do that, well, the tau xy, we already know from TC and J that this is what that quantity is. All right, and we can figure out what the magnitude, right, of, let's say, the state of principal stresses, right? So what are the sigma 1 and the sigma 2 here? We can figure this out by doing some more work with Mohr circle, right? So we started off where? Well, Mohr circle is where? It's at the origin because there are no, right, sigma x plus sigma y, sigma x is equal to 0, sigma y is equal to 0 in this case, right? So that's going to be 0, so it's just a Mohr circle at the origin. And we're in a state of maximum shear stress, right? That's what this is. There are no, it is maximum, all right, because it's pure shear. So in that orientation, it's maximum. And sigma x and sigma y are 0. Right? In general, when sigma x and sigma y are equal to each other, you're going to have a state of maximum in-plane shear stress. Okay. So we're up here. How do we get to our state of principal stresses? We've got to rotate, right, to the appropriate location. Okay, so that's what we do. We got to either go here or here, like that. And this is just the radius, and this is just the radius to get to there. Yeah, so this was the original state. Right. Okay, then we rotate over here, right? And we know that now our sigma 1 is equal to tau xy, or tau, and sigma 2 is equal to minus tau. Okay, and the rotation was 45 degrees of the actual element, but 90 degrees on Mohr's circle. So this is what that state looks like. Okay, any questions on this? These are two important cases, right? We've now related uniaxial testing to a maximum in-plane shear stress. We've related a pure shear to normal stresses that could develop. Okay? So if you have material that fails because of normal stresses, even though it's under pure shear, you can figure out, okay, is it going to fail or not? If you have a material that's under uniaxial loading and it fails because of shear predominantly, you can figure out what the equivalent shear stress is and figure out if it's going to fail or not. Okay, so yes, this is kind of a classic example using a cylindrical pressure vessel. And what do we know? We know that sigma 1 is going to be twice of sigma 2, right? Because we have a hoop stress there where it is, and we have a longitudinal stress, right? So we can figure out what the average stress is between those, or the average normal stress, okay? And we have, at least in the original orientation, we have tau equal to 0, okay? And so we can plot out this Mohr circle, which kind of looks like this. The radius is going to be PR over 4t, and we can figure out what the maximum shear stress is going to be. The maximum shear stress is just going to be, up here or down here, okay, and that's going to be the radius. Okay. And we do that, and we get the following, right? So again, pressure vessel. We didn't think, right? We were like, hey, there's no shear stress here. It's just happiness. We have normal stresses. No, there are equivalent shear stresses involved with a cylindrical pressure vessel. But what happens for a spherical pressure vessel? What are the sigmas for a pressure vessel?
Everything's PR over 2T.
Everything's PR over 2T, all right? What are the shear stresses here in an original state, or any state? Okay, so what does Mohr's circle look like?
PR over 2T.
Let me see if I...
One half on either side.
Okay, so here's tau.
PR over 4T.
So you just told me that we have sigma 1 equals PR over 2T. Sigma 2 also equals PR over 2T. Tau is equal to 0, right? So let's say, all right, so the average, what is sigma average?
So we have PR over 2T.
PR over 2T, right? Okay, so here's sigma average. Okay? Now plot the point. Let's plot point sigma 1 tau. Where is that? Oh, so first off, this is the center, right? Okay, where's sigma tau? It's right there. It's not, it hasn't moved. It's still right there. So for this case, the entire Mohr circle is a point. There's no shear stress. The spherical pressure vessel. Okay? It turns out that's not completely true. We'll talk about that tomorrow. When you talk about absolute maximum shear stress, it's different. But the maximum in-plane shear stress is 0. Okay? That's fun. So this is kind of a fun problem that I put on exams that gets people upset. All right? So what did we do today? We talked about the derivation of Mohr's circle. We talked about a method of constructing Mohr's circle. And we did some examples. Welcome to mechanics. You now know Mohr's circle. Well, you're now going to be examined on Mohr's circle. You're now responsible for knowing Mohr's circle. So you've now crossed this beautiful rite of passage. And it's a useful tool that just shapes now how you think about, is it going to break or not? That's what it does. Right. Thank you.